Yeah, good morning, one and all. Today, the most important topic of this unit 4 counters. We will study only 4 counters from this chapter. At least 2 counters will appear in your examinations. Very straight questions will come into your question paper. Okay. Before going to see different types of counters and their design and their performance, let us first have a look at what do you mean by counter. The definition of counter goes like this. A counter is nothing but a register that goes in a prescribed sequence. See, the name itself will tell you counter. What counter do you know? Counter will simply counts. It counts. For example, you take a 4-bit register. I am taking a 4-bit register. For example, my register is this one. What do you mean by 4-bit register? A 4-bit register is a register with 4 flip-flops. A 4-bit register contains 4 flip-flops because already in registers we have come across. We understood what do a register, what is a shift register, how serial transfer happens, etc. Now we see what do you mean by counter. Counter counts. A counter is nothing but a register that goes in a prescribed sequence. For example, I take a 4-bit register. The 4-bit register consisting of 4 flip-flops. For example, my register at present is having 0, 0, 0, 0 in it. Because 1, 2, 3, 4 flip-flops, all flip-flops have clock inputs. See, this is a register with 4 flip-flops. Every flip-flop have a clock. For example, if you press the clock, what happens? For example, if it goes to 0, 0, 0, 1, again you press the clock, it goes to 0, 0, 1, 0. Again you press the clock, it may go to 0, 0, 1, 1. Again you press the clock, 0, 1, 0, 0. Again you press the clock, and so on and so forth. Finally it comes to 1, 1, 1. Means my register start counting from 0. After a clock pulse, go to 1. After a clock pulse, go to 2, go to 3, go to 4, and so on. Finally, it has come to 15. If you give clock again, it goes to 0, 0, 0, 0. Because after 4 ones, there is nothing else. So this is called 0. See, if you see this register, whenever clock is pressed, going in a specific sequence. So 0 to 1, 1 to 2, 2 to 3, 3 to 4, 4 to 5, and so on. It goes to 15. From 15, it goes back to 0. This we call it as a prescribed sequence. Means the transitions of a register is going in a meaningful way. For example, if there is a register which counts like this 0, 1, 7, 5, 2, 8, 16. If a register counting like this, we will not call it as a prescribed sequence. So a prescribed sequence means a sequence which makes some sense. You see here, what is the sequence here? This is called binary sequence. Means my register is going in binary sequence because it's going from binary 0 to binary 1 to binary 2 to binary 3 to binary 4 and so on and so forth. Binary 15, 1, 1, 1, 1 is called binary 15. Again, it's going to binary 0. Again, it start counting 0, 1, 2, 3, 4. So if any register which goes in a prescribed sequence, we will call it as a counter. Understand? That is the definition of counters. Got it? Now we will see how many types of counters are can be studied. See, by their nature, counters are of 2 types. One is called ripple counter. The second one is called synchronous counter. By their nature, counters are of 2 types: ripple counter, synchronous counter. See, just now I have explained you what do you mean by counter. A counter is nothing but a register. What do you mean by register? A register is nothing but group of flip-flops. A register is nothing but group of flip-flops. Means a counter is nothing but register. Register is nothing but group of flip-flops. So what do you mean by ripple counter? A ripple counter is a counter where there is no common clock. Means, see here in ripple counter we have group of flip-flops. Every flip-flop have a clock. If all the clocks does not have a common clock, we call it as ripple counter. Whereas in synchronous counters, we will have common clocks. I'll show you an example of ripple and I will show you an example of synchronous counters. How does ripple? For example, I have a counter, for example, a 3 flip-flops are there called as A, B, C. All are of type T. Let us take an example. The first clock is coming something from clock. The second clock coming from first flip-flop output. The next clock is coming from an AND gate where one input is coming from this one. The second input is coming from this one. See, there are 3 flip-flops A, B, C, and these are the clock inputs of the flip-flops. The first flip-flop clock input is coming from clock. Second flip-flop clock input is coming from A. Third flip-flop clock input is coming from something like B and A. Means the clocks are not connected to common source. That is called ripple. In ripple counter, there will be no common clock. If you take a synchronous counter, for example, if you take a synchronous counter, 1, 2, 3 flip-flops, every flip-flop have a clock. All, let us take an example, all flip-flops of type T. This is a clock, this is a clock, this is a clock. The name of this flip-flop is A, the name of this flip-flop is B, the name of this flip-flop is C. For example, you see, all flip-flops clock C. The clock of first flip-flop, the clock of second flip-flop, the clock of last flip-flop, all are connected to the same line. We call it as common clock. That is the difference between ripple counter and synchronous counter. In ripple counter, there will be no common clock. In synchronous counter, there will be common clock. So by looking into a given diagram, one can understand whether it is designed using ripple fashion or designed using synchronous fashion. So we have to study ripple counters as well as synchronous counters. Okay. Now you see this counter is counting binary numbers. We call it as a binary counter. For example, if there is a counter which counting BCD numbers, we call it as BCD counter. So in ripple counter, we will study 2 types. In synchronous counter also, we will study 2 types. In ripple counter, we will study binary ripple counter and BCD ripple counter. In synchronous also same way. Binary ripple counter, BCD ripple counter. So total 4 counters we have to come across. Binary ripple counter, BCD ripple counter, binary synchronous counter, BCD synchronous counter. Let us start first the first model, that is called binary ripple counter. What do you mean by binary ripple counter? First point, it is a ripple counter. First we have to understand it is a ripple counter. What do you mean by ripple counter? Since it is a ripple counter, there will be no common clock. And it is binary in nature, means it counts binary numbers in sequence. A binary ripple counter, it's a ripple counter. It does not have a common clock. It counts binary numbers. For example, if you use n flip-flops, see here I did not specify the size of the counter. For example, if you specify there are n flip-flops, then it can count from 0 to 2 to the power of n minus 1. For example, I have been using 4-bit counter. Means I am using 4 flip-flops. How many flip-flops I am using? 4 flip-flops. Means 1, 2, 3, 4. Starts from 4 zeros and counts till 1, 1, 1, 1. Yes or no? For example, if I am using a 4-bit counter, means 4 flip-flops, we will start with 4 zeros and ends with 4 ones. Because 4 flip-flops, the starting value is 0, the last one is 15. See, that's what I wrote here. If you use n flip-flops, it can count from 0 to 2 to the power of n minus 1. In this example, I have been using 4 flip-flops. 4-bit counter means 4 flip-flops. Means the counting will be from 0 to 2 to the power of n. Means 4 minus 1 means 0 to 15. See, 0 to 15. This is how we will understand a binary ripple counter. Now we have to see how do we design it. Now the logic is, how do we design? For example, let us first look at how binary sequence goes on. For example, if you see binary number, a ripple binary counter, it starts from 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Okay, let us take an example. I have been using 4 flip-flops. I will call them as, for example, the first flip-flop, I call it as A3, A2, A1, A0. See, it is a 4-bit binary ripple counter with 4 flip-flops. First flip-flop is called A3, second flip-flop is called A2, next flip-flop is called A1, last flip-flop is called A0. So it goes from 0, 0, 0 to 1, 1, 1, 1. Now, since it is a ripple counter, we have to observe how flip-flops are changing. Let us first focus at A0. The first flip-flop is called A0. See, it is 0 first, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1. Means first flip-flop A0 is changing every time. So see, I will take a first flip-flop. The name of the flip-flop is A0. See, I am using T flip-flops here for the construction. This is my clock input. I will connect to a value called as count. See, for this clock input, there is 0, a bubble before. We call them as negative edge triggered flip-flops. Means the flip-flops where there is a bubble before clock input, we call it as a negative edge triggered flip-flop. For example, this flip-flop will be, see, this flip-flop will be triggered if the value of count is 0. For example, when count is 0, means if you press the count, if count makes 0, means the 0 complement is 1, the clock becomes active. Means when does the clock of this flip-flop is active? When count is 0. Means that's why we call it as a negative edge triggered flip-flops. Let me first finish the diagram, then you'll understand. 1, 2, 3, 4. All are flip-flops of type T only. All T inputs are connected to logic 1. What is this line? This is called logic 1. This is called logic 1. Means every flip-flop is connected to, all flip-flops are T type. This is called A1. This is called A2. This is called A3. For example, okay? And now you see, since flip-flop A is complementing every time I have connected this. See, since T is 1. So let us have a look at the characteristic table of T flip-flop. What is the characteristic table of T flip-flop? T versus Q of T plus 1. When T is 0, next state is present state. When T is 1, next state is complement of present state. Means if you want to complement the present state, the T must be 1. See, the T, all T's are connected to logic 1. Means every flip-flop is ready to complement. But waiting for what? Waiting for the clock. The first flip-flop clock is connected to counter. Whenever count is 0, this flip-flop gets complemented. Now you come here. See A1 0 0 1. See when A1 is complementing, see A1 going from 0 to 1. When A0 goes from 1 to 0. Means I will connect A0 to the clock input of this one. This is my clock. See A2 0 0 0 0 1. Means A2 complements when A1 goes from 1 to 0. So, this is my clock. Next, you see 0, 0, 0, 0, 0, 0, 0, 0, A3 going from 0 to 1 when A12 goes from 1 to 0. So, that's all. This is binary counter. This is binary ripple counter. For example, I will explain you. For example, with an example. For example, right now I am having 0, 0, 0, 0 in it. See, this is I have started my counting with first value. Every flip-flop is filled with zeros. For example, I made count to be 0. Count 0 is 7. 0 complement is 1, means this clock is active. Since this clock is active, already the T is 1. See, the value of T is 1. Clock active. Hence, I told you, when T is 1, next state is complement of present state. Since T is 1, clock is active, the first state becomes 0, becomes 1. Means what is the value of A0 now? 1. See, this 1 comment comes here. So if this is 1, the complement means the clock input is not. See, 1 bubble in the cavity, 1 complement is 0, means this clock is inactive. If this clock is inactive, there will be no value in A1. See, if this flip-flop is inactive, this flip-flop is inactive. If this is inactive, this is inactive. See, after 0, 0, 0, 0, next value is 0, 0, 0, 1. See, 0, 0, 0, 1. Understand? Let us take one more example. I have been using 1, 1, 1, 1, last state. Means all my flip-flops are at present is having 1s in it. For example, now you make count 0. Since 0 complement 1, this clock is active. If this clock is active, this flip-flop complements 1 to 0. Means A0 becomes 1. If this A0 becomes 1, this clock is active. So this 1 becomes 0. Means this A1 is 0. If 1 is 0, this clock is active. Since this clock is active, T is 1. This 1 becomes 0. Means A2 also 0. If A2 is 0, 1 complement 0 complement is 1, this clock is active. Since this clock is active, T is 1, 1 becomes 0, A3 is 0. Means earlier I took 1, 1, 1, 1. Now the state is 0, 0, 0, 0. That is called, from 15 it go back to 0. Is it clear? Is it clear? Amma, is it clear?
Yes, sir. Yes, sir.
Okay, okay. This is called binary ripple counter. Okay. Next, let us go to BCD ripple counter. The next topic is BCD ripple counter. What do you mean by BCD numbers? What do you mean by BCD? BCD numbers starts from 0, and then what is BCD? BCD stands for binary coded decimal form. So in BCD, we will start counting from 0 and ends at 9, because decimal number ends at 9. So for example, 0 to 9 means 10 combinations. 10 is less than or equal to t power n, means n is equal to 4. So my BCD number starts from 0. 0 go to 1, 1 go to 2, 2 go to 3, 3 go to 4, 4 go to 5, 5 go to 6, from 6 we go to 7, from 7 we go to 8, from 8 we go to 9. There are many combinations, but we will not count, because it starts from 0 and ends at 9. From 9 it goes to again 0, because BCD number starts from 0 and ends at 9. Understand? Now let us see the state diagram for BCD counter. The BCD ripple counter. Just give me a minute. Aidu. Zero 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 one 00102. From 2 we go to 3. From 3 we go to 4. From 4 we go to 5, 6, 7, 8, 9. From 9 we go to 0. Understand? Means we have like this: 0 0 0 0 1 2 3 4 5 6 7 8 9. So this is the sequence. This is the sequence. The first flip-flop is called Q1. Second flip-flop is called Q2. The next flip-flop is called Q4. The next flip-flop is called Q8. See, I have been using 4 flip. See, Q8, Q4, Q2, Q1. This is flip-flop Q8. This is Q4. This is Q2. This is Q1. So I have been using 4 flip-flops. Now you look at Q1. What happened to Q1? 0, 1, 0, 1, 0, 1, 0, 1. I forgot write 8 in between. This is not this is 0. See, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1 means Q1 complements every time. So what can we write here? We can derive some rules. Let us first discuss about Q1. Q1 complements every time. That is what about Q1. Okay. Now let us try to understand Q2. See Q2. Q2 is 0 here, 0 here. No change. Q2 is 0 here, 1 here. See, means Q2 complements when Q1 goes from 1 to 0. See, this is Q2. 0, 0, 0, 1 means when Q1 goes from 1 to 0, Q2 complements. So Q2 complements when Q1 goes from 1 to 0. That's what you understand. Means see, Q2 complements when Q1 goes from 1 to 0. So 1 1 same 1 0. Q2 complements when Q1 goes from 1 to 0. Very good. Again 0 0 same. 0 1. Well, again complement. See, Q2 complements when Q1 goes from 1 to 0. Again same, no problem. Q2 complements when Q1 goes from 1 to 0. When Q1 goes from 1 to 0, Q2 complements. Again 0 0. Okay. Again, you see, you can see here. We will look at second from 1 1 1 0. See, since Q1 going from 1 to 0, Q2 complements. Again 0 0, no change. 0 1, no change. When Q2 goes from 1 to 0, Q1 complements. Q2 complements. 0 to 1, no change. 1 to 0, Q2 complements. Again 0 to 1, no change. See, when Q1 goes from 1 to 0, Q2 complement avvala ikkada avale chudandi. When we are going from 9 to 0, see, Q2 is 0 to 0. Unfortunately, Q1 is going from 1 to 0. Means this rule holds till this place, but not at this place. So I want to write one more rule for Q2. I want to write, see, I'll write one more rule for Q2. Then you will understand. Q2 complements every time when Q1 goes from 1 to 0. As long as Q8 is 0. Means ఇక్కడ ప్రాబ్లం ఏమొచ్చింది, Q8 0 వచ్చింది, ఇక్కడే కదా ప్రాబ్లం వచ్చింది. See, 0 to 0, 0 to 1, no change. But when Q1 goes from 1 to 0, Q2 should complement, but it's not happening because Q8 is 1. That's what second rule for Q2. Q2 remains at 0 as long as Q8 is 0. So there are two rules for Q2. Similar way, let us look at Q4. See, 0 0 0 0 Q4 0 to 1 వచ్చింది చూడండి. When Q2 goes from 1 to 0, Q4 complements. మళ్ళీ ఇక్కడ చూడండి, ఇక్కడ వచ్చింది. Q4 complements when Q2 goes from 1 to 0. So the rule for Q4 is Q4 complements when Q2 goes from 1 to 0. So Q4 rules is also over. Now let us look at Q8. What is the rule for Q8? Okay. Chundi, Q8 is 0 0 0 0 0 0 0 0. Because see, this is Q8, this is Q4, this is Q2. Here you see, Q8 remains at 0. See the rule. As long as either Q2 or Q4 is 0. 0 0 0 0 0 1 0 1 1 0 1 0 1 1 1 1. Means till here we can understand. See, Q8 remains at 0 as long as Q2 or Q4 is 0. Understand? The rule is, let me write the rule. Q8 remains at 0 as long as Q2 or Q4 is 0. రెండిట్లో ఎవరో ఒకరు 0 ఉన్నా కూడా Q8 0. చూడండి, Q8 is 0 here, 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 0 here. Because Q0 0, 0 0, 0 1, 0 1, 1 0, 1 0 means still here. The over. The next one means ఈ 4 states ని మనం ఇప్పుడు డిఫైన్ చేయాలి. When Q2 and Q4 both become 1 means రెండు ones అయితే. When Q2 Q4 both becomes 1, Q8 complements when Q1 goes from 1 to 0. చూడండి ఇప్పుడు చూడండి, Q8 0 0 చేంజ్ అవ్వలేదు ఎందుకంటే Q1 going from 0 to 1, no change. See, from 0 to 1, see, Q8 is now changing because my Q1 is going from 1 to 0. Again 1 1 because Q8 is not changing. So till here 1 2 3 4 5 6 states. For all these 6 states, either Q2 or Q4 is 0, hence my Q8 is 0. Q8 remains at 0 as long as Q2 or Q4 is 0. Once Q2 Q4 both becomes 1, Q8 complements when Q1 goes from 0. So all states have been explained using these rules. Now it is a responsibility to draw BCD ripple counter design. I will draw the design first, and let us assume whether all rules specified were met or not. That is the logic. See, let me first draw the diagram for you. Then we will see whether all rules discussed have been designed or not. For example, I have been using 4 JK flip-flops for this design. 1, 2, 3, and 4. See, all flip-flops are of type JK. It is a JK flip-flop. It is a JK flip-flop. It is also JK flip-flop. What is the name of the first flip-flop we have come across? Q1. Second flip-flop is called Q2. This is called Q4. This is called Q8. This is called Q8. Let me first finish the design, then we will understand. Okay. This line is called logic 1. The first flip-flop J and K both are connected to logic 1. Okay. This flip-flops K is connected to logic 1. Q4's both flip-flops are connected to logic 1. This is connected to logic 1. Only second flip-flops Jth input, 8th flip-flops Jth input only not connected to logic 1. I will show you why like that. So, what is the rule for Q1? Q1 complements every time. That is your rule. Because I hope you remember the characteristic table of JK flip-flop, J versus Q versus Q of T. When JK 0 0, next state is no change. When JK 0 1, next state is 0. When JK 1 0, next state is 1. When JK 1 1, next state is complement of present state. Means when J is 1, when K is 1, the next state is complement. See, since J is connected to 1, the K is connected to 1, this flip-flop is ready to complement. Waiting for what? Clock. See, I have been using a count pulse. It is also negative edge triggered flip-flop. Means when count is 0, the clock is active. This flip-flop gets complemented every time because J is connected to 1, K is also connected to 1. Okay. Now let us go to Q4 first. Q2 let us first Q2. What is the rule? Q4 complements when Q2 goes from 1 to 0. Means this Q4 complements when Q2 goes from 1 to 0. See, the Jth input, Kth input of Q4 flip-flop are connected to logic 1. Means this flip-flop is ready to complement. Waiting for what? Waiting for Q2 to be 0. So I will add the clock of Q4 connected to Q2. See, this J is connected to 1. K is also connected to 1. This flip-flop is ready to complement. Waiting for what? Clock. When the clock becomes active, when this line is 0. This line is 0 means Q2 must be 0. That's what I wrote. Q4 complements when Q2 is 0. So whenever Q2 becomes 0, this clock is active. Since J and K are 1 1, Q4 complements. This is how we have to understand this diagram. Next, let us now first look at Q2. See what did I write for Q2? See, Q2 complements when Q1 goes from 1 to 0 as long as Q8 is 0. As long as Q8 is 0. Okay? Means Q2 complements when Q1 goes from 1 to 0. When Q1 goes from 1 to 0. So I will connect Q1 to its clock. Because whenever you want to complement Q2, we want Q1 to be 0. That's why I have connected to this. What is the extended rule? As long as Q8 is 0. So that's why I take complement of Q8 and connect here. See the rule? As long as Q8 is 0. Means when Q8 is 0, this is a complemented output of the flip-flop. So when Q8 is 0, this becomes 1. If this becomes 1, J becomes 1. K is already connected to 1. When JK flip-flop both are 1, 1, it's ready to complement. Waiting for what? Clock. The clock is Q1. That's what I wrote. When Q8 is 0, Q2 complements when Q1 is 0. First rule is over. What is the next rule? Q2 remains at 0 as long as Q8 is 0. You see here, Q2 remains at 0 as long as Q8 is 0. What happens when Q8 is 0? What is this? Q2 remains at 0 as long as Q8 is 0. But for example, when Q8 is 0, this 1 becomes 1, 1 and 1 complement, so it will be remain states at 0. Now let us go to Q8. See, Q8 remains at 0 as long as Q2 or Q4 is 0. This we have to incorporate now. Means the J I will connect to an AND gate. One input comes from Q4. The second input comes from Q2. See, when Q2 is 0, Q4 is 0, what happens? 0, 0. When this is 0, this is 0, this becomes 0. Means J becomes 0, K becomes 1. Okay. The clock is connected to Q1. See, the clock is connected to Q1. See the rule? Q8 remains at 0 as long as Q2, Q4 is 0. See, for example, when Q2 or Q4, any one of them is 0, this J input becomes 0. If J is 0, K is 1, we know for JK flip-flop, J 0, K 0, what is next one? 0. See, Q8 remains at 0 as long as Q4, Q2 is 0. When both Q2, Q4 becomes 1, Q8 complements when Q1 goes from 1 to 0. See, when Q2 is 1, Q4 is 1, means this is 1, this is 1, J becomes 1, already K is 1, this is ready to complement and waiting for what? The Q1 to be 0. See, when both becomes 1, Q8 complements when Q1 goes from 1 to 0. That's all. So this is how the diagram, we have derived some rules out of the diagram, and all those rules have been included in the design of the BCD ripple counter. This is how we will understand BCD ripple counter. Now let us move to the next type of counter, that is called synchronous counters. What do you mean by synchronous counter? Synchronous counter means, okay, I will write synchronous binary counter. Synchronous binary counter. First point, it is synchronous in nature. Means there will be common clock. See, since it is synchronous, there will be common clock. Means all flip-flops gets common clock input. All flip-flop gets common clock input, and it is binary in nature. It is binary in nature, means it start counting from 0 to 2 to the power of n minus 1 if number of flip-flops are n. Same in that చెప్పినట్టే. If there are n flip-flops, it counts from 0 to 2 to the power n minus 1 because it is binary in nature. Synchronous binary counter, that is the logic. Okay. In synchronous binary counter, the logic is very simple. Since it is synchronous, we will use common clock mechanism, and all flip-flop gets common clock input. Since it is binary counter, it counts from 0 to 2 to the power n minus 1 if number of flip-flops are n. Understand? Now let us see the design of the. Now let us see the design of this one. For example, how binary counter looks like, how binary transition takes place. Binary counters 0 0 0 0 0 0 0 1 0 0 1 0 0 0 1 1 0 1 double 0 0 1 0 1 0 1 1 0 triple 1 8 9 10 11 12 13 14 15. Let us call these flip-flops as, see the names of the flip-flops is like this. The first flip-flop is called A3, A2, A1, A0. There are 4 flip-flops, A3, A2, A1, A0. You see A0, what happens? 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, back to 0. Means A0 complements every time. What did you understand? A0 complements every time. See, synchronous counter, every flip-flop gets a common clock. See, 0, 0, 1. See, when A1 becomes 1, A1 complements when A0 is 1. See, A1 complements when A0 is 1. 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 Now you see A2, 0, 0, 0, 0, 1. A2 complements when A0, A1 both are 1. A2 complements when A0 is 1, A1 is 1. Again see, 1, 1, 1, 1. Again it got complemented. A2 complements when both A0, A1 are 1. Again 0, 0, 0, 0, 1. See, again when A0 is 1, A1 is 1, A2 complements. Now come to A3, 0, 0, 0, 0, 0, 0, 0. Here there is a complementation. See, A3 complements when A0, A1, A2 all are ones. This is the rule for synchronous binary counter. A0 complements every time. A1 complements when A0 is 1. A2 complements when A0, A1 both are 1. A3 complements when A0, A1, A2 all are ones. Is it clear? Is it okay? Now see, from these deliberations, I am going to construct synchronous binary counter. I am going to design the synchronous binary counter from these deliberations. Okay. I have been using 1, 2, 3, 4 flip-flops. All flip-flops of type JK only. All flip-flops of type JK. See, since this is a synchronous counter, what do you mean by synchronous counter? In synchronous counters, we will have common clock concept. So, no confusion. All clocks C. All clocks are connected to common clock. Okay. The first flip-flop is called A0. This is called A1. This is called A2. This is called A3. A0, A1, A2, A3. So what did you understand from this diagram? A0 complements every time. A0 complements every time. So when does the JK flip-flop complements? The JK flip-flop complements when J and K are 1, 1. When J is 1, K is 1, JK flip-flop complements. So from this transition, our deliberation was A0 complements every time. How do we complement A0 every time? Because common clock anyway gets fired. We have to make the both J and K as 1 and 1. See, this is my count. This is my count pulse. This is my Count pulse. Means when count is 1, the J becomes 1, K becomes 1. When you press the clock, A0 complements. Now you see, when does A1 complements? A1 complements when A0 is 1. Means, see, I will take an AND gate here. One line from counts, the second line from come A0. Means when count is 1, A0 is 1, 1 and 1, the JK becomes complement. See, A1 complements when J is 1, K is 1. J and K becomes 1 and 1 if this AND gate is 1. This AND gate becomes 1 when A0 is 1 and count is 1. See, anyway, we will, every time we will press count and press clock. But the J and K to be 1 and 1 if and only if A0 is 1. Same way, let us try another AND gate. One line coming from this, the other line is coming from 2. This is connected to the JK. See, means this flip-flop A2 complements when J is 1, K is 1. J and K becomes 1 and 1 if this AND gate is 1. This AND gate is 1 because when A1 is 1. And when A0 is, means when A0 is 1, A1 is 1, count is 1, this A2 complements. Same way, A3. So take another complement, another AND gate. One input comes from this gate, the other input is coming from A2, this is connected to J. A3 complements when J is 1, K is 1. J and 1, K becomes 1 and 1 if this AND gate is 1. This AND gate becomes 1 when A2 is 1. This AND gate, this input becomes 1 when with the AND gate 1. This AND gate becomes 1 when A1 is 1. This AND gate becomes 1 A1. Means when A0 is 1, A1 is 1, A2 is 1, J and K becomes 1, 1, A3 gets complemented. So this is synchronous binary counter design. The design of synchronous binary counter looks like this. Now we will see the next counter, the fourth counter, that is called as synchronous BCD counter. That is called as synchronous BCD counter. Means we have to design a binary BCD counter in a synchronous fashion. Okay. Let us first draw the test. Since it is a synchronous counter, we have to follow the design procedure. For example, Q8, Q4, Q2, Q1. I have 4 flip-flops. Their present states Q8, Q4, Q2, Q1. Their next states. See, these are called present states. These are next states. Because we know it is a BCD counter. Starts from 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So there are 0 to 15, 16 states. What is the state C? In BCD counter design, 0, 0, 0, 0. What is the next state for 0? 1. 0 goes to 1, 1 goes to 2, 2 goes to so. So I will write the next states in sequence in this table. So 0, 0, 0, 0. What is the next state for 0? 1. For next state for 1, 2, 3, 4, 5, 6, 7, 8, 9. For 9, what is the next state for 9? 0 go to 1, 1 go to 2, 2 go to 3, 3 go to 4, 5, 6, 7, 8, 9. 9 go to? Someone should answer. 9 go to 0. 10. There is no next state for 10. So cross, 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 cross. Next states for these states have not been included since it is a BCD counter. For 10, no next state. For 11, no next state. For 12, no next state. For 13, 14, 15, the next states have not been defined. So that is we have to understand. Okay. Now, before going to fill this table, let us first recall excitation table of T flip-flops. What is an excitation table? Excitation table is a table to know the value of the flip-flop inputs provided present state and next state. When present state is 0, next state is 0, T0. Present state is 0, next state is 1, T1. Present state is 1, next state is 0, T1. Present state is 1, next state 1, T0. Means when present state and next state are different from each other, T becomes 1. When present state and next state are same, T becomes 0. That we have to understand. So now we have to extend this diagram for writing flip-flop inputs. Okay. I will call them as TQ1, TQ2, TQ4, TQ8. Sorry, TQ8, TQ4, TQ2, TQ1. See, now we have to write what is Q8 present state. This is present state 0, next state is 0. So we know when present state is 0, next state is 0, T is 0. Means present state and next state are same, 0. 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, it's 0, 0, 0, it's 0, 0, 0, it's 0, 0, 1, it's 1, 1, 1, it's 0. Okay, this is cross, 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 because we don't know what happens to the next values. See, this is 1, this is 0, this is sorry, this is 1. 1, 2, 3, 4, 5, 6 crosses. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 values and 6 crosses. Understand? Next, we will see next one. 0, 0, TQ for 0. 0, 0, TQ for 0. 0, 0, TQ for 0. 0, 1, TQ for 1. 1, 1, 0, 0, 0, 0, 0, 0, 1, 0, 0, 1, 0, 0. Even cross line. Next, let us go to TQ2. See, 0, 0, 0, 1, 0, 0, 1, 0. Next, 1, 0, 1, 1, 0, 1. Next, 0, 1, 0, 0, 1, 0, 0. 0, 1, 0, 1, 0, 1, 0, 1, 0, 0. Now you see here, Q1, 0, 1. Marpin 1, 0, 0, 1, 1, 0. 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1, 0. Means TQ1 is always 1 because the present state and next state is continuously being complemented. So now this table is ready. Now we have to identify the equations for TQ8, TQ4, TQ2, TQ1. See, TQ8, TQ4, TQ2, TQ1 are function of 4 variables Q8, Q4, Q8. See. Now I will find out what is TQ8. So take a 4 variable Karnaugh map. Q8, Q4, Q2, Q1, 0, 0, 0, 1, 1, 1, 1, 0, 0, 0, 0, 1, 1, 1, 1, 0. See, find out what is TQ8. 0, 0, 0, 0, 4 zeros, 0, 0, 0, 1, 0, 0, 0, 0, 0, 0, 0, 1. Next, 0, 1, all crosses. 0, 1, cross, 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 cross. So this makes a quad, this makes a pair. So TQ8 is equal to, for this quad, Q8, Q1 plus for this pair Q8 gone, Q4, Q2, Q1. So TQ8 is obtained. Now we have to obtain TQ4. What is TQ4? Very simple. Take again a 4 variable Karnaugh map. Q8, Q4 on rows, Q2, Q1 on columns, 0, 0, 0, 1, 1, 1, 1, 0, 0, 0, 0, 1, 1, 1, and 1, 0. See the values 0, 0, 0, 1, 0, 0, 0, 1, 0, 0, all cross. See, 0 0 0 1 0 0 0 1 0 0 cross 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 cross. What can we make? A quad. So Boolean function for TQ4 is equal to Q2 Q1. In the similar way, find out for TQ2. Amma, I'll finish this within 10 minutes. Don't worry. Q8, Q4, Q2, Q1, 0 0 0 1 1 1 1 0 0 0 0 1 1 1 1 0. See TQ2 value 0 1 0 1 0 1 0 1 0 0 and send 0 1 0 1 0 1 0 1 0 0 cross 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 cross. What can we do with this? Nothing else. TQ2 is equal to, if this is a quad, Q8 bar Q1. What is the equation for TQ1? You see TQ1 1 1 1 1 1 1 1 1 1 1 cross 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 cross. So if you treat all of them as 1, my TQ1 becomes 1. See, now I got equation for TQ8, TQ4, TQ2 and TQ1. Now I will draw BCD counter.
Sir, can you show TQ4, sir?
Is it okay? Now you see BCD counter. So I have been using 1, 2, 3, 4, all flip-flops of type T. The output is called Q1, Q2, Q4, Q8. I have 4 flip-flops. All flip-flops, see, I have 4 flip-flops, Q8, Q4, Q2, Q1. All are of type T only. So T flip-flops. Now we have to connect. See, since this is a synchronous counter, all flip-flops receive common clock because it is synchronous. This is synchronous counter. So every flip-flop receives common clock. Now we have to connect Q1. What is TQ1? See, TQ1 is nothing but logic 1. What is TQ2? TQ2 is Q8 bar Q1. So this is Q1. Q8 bar. See, Q8 bar and Q1. What is TQ4? TQ4 is Q2 Q1. So take an AND gate. This is Q1. This is Q2. Q2 Q1 over. What is TQ8? Q8 Q1 means take 2 AND gates, give them to an OR gate and connect. See, two terms Q8 Q1. One line shall come from Q1. The second line shall come from Q8. So Q8 Q1. Next is Q4 Q2 Q1. See, this is Q1. Any chance of Q2? Yes, this is Q2 and this is Q1. Q4 Q4. See, the equation is Q4 Q2 Q1. Already what is connected? Q1 is connected. Q2 is connected. We have to connect Q4. So this is how the synchronous BCD counters have been declared. Is it clear? Is it clear?
Sir?
Yes, please. Yes,
sir,
please.
Yes, sir. Now it's clear, sir.
TQ2, TQ4.
Sir, diagram is somewhat confusing, sir.
See, once you have equations, we can connect it. Don't worry about it, okay? Got my point? Okay.
Yes, sir.
Otherwise, we can draw a diagram in a different way also. Do you want me to draw an alternate way of drawing this diagram?
Yes, sir.
1, 2, 3, 4. All are of type T only. T, T, T. What is this called as? What is this line? Q1. Q2. Q4. Got it? First line is called Q1, Q2, Q4, Q8. So since this is a synchronous counter, all flip-flops receives common clock. So clock, clock, clock. What is TQ1? Logic 1. No change. So this is connected to 1. That we call it as logic 1. What is TQ2? Q8 bar Q1. So take an AND gate. One line from Q1. The second line comes from TQ bar 8. See, Q8 bar Q1. This line is Q8, Q8 bar and Q1. What is this? This is Q1, Q2, Q4, Q8. Now tell me what is TQ4? Q2, Q1. Q2. So take an AND gate. One line from Q2, the second line from Q1. Now what is the last one? What is TQ8? Q8, Q1 plus something, something. So take two AND gates, put them to OR gate. So the first equation is Q8, Q1. Means one line from Q8, second line from Q1. Next Q4, Q2, Q1. One line for Q1, Q2, Q4. Is this simple?
Yes, sir.
Okay. See, there are varieties of ways of drawing diagram. Don't worry about that. See here, if the lines are pending here, we can draw it easily. No problem. See, there are only two more topics from this chapter. That is called, see, this chapter is almost over. We have left with this unit. We have two special counters to be designed. One is called ring counter. The next one is called as Johnson counter. Two special counters to be discussed in this unit. Then unit 4 will be over. Your academic calendar have been extended till 23rd January. Okay. So you will be having classes till 23rd January. And another interesting point is all mid examinations of second mid are offline. All mid examinations are offline. Another important point. And all lab examinations are also, lab external examinations are also offline. Is it clear? I hope today,
Sir, second meet also offline, sir.
Second mid only, first mid is over now already.
Yes, sir.
I think today my book is clean and not blurred, right?
Yes, sir.